I'm just recording my screen, or I guess not my screen, my video from my webcam and my sound. So I'm gonna try to repeat questions you guys have, or if you have anything in the chat, I'll try to repeat that so that everyone watching later can see it. But I'm not recording you guys because I know that's kind of weird. Okay, so let's get something to take notes with. If you have your notebook from last year, that'd be perfect. If you don't, grab some loose leaf paper or another notebook or something like that, and we gonna get going, you guys. I gotta get my energy up. I'm tired. How's everyone doing for that? Uh-huh. I did get your corrections, yes. Mm-hmm. They're not due until next week, but thank you. I appreciate it. Oh, okay. When we're all ready for note taking, give me like a thumbs up or some sort of sign. Looks good. Awesome, awesome. Looks like everyone's ready, I think. Kai, how about you? Uh-huh. Okay. You ready for note taking? Okay, here we go. So, the whole idea is that what we're starting is a new unit. I guess in Physics 1 it would have been called Unit 5. Or now it's 1, I guess. Rotational motion. And the whole thing about this unit, the way I've designed it, is that I am going to try to go through everything we did last year really briefly, and we redo it in its rotational version. So we start with kinematics and the equations of motion, and we move on through forces and energy and momentum, and well, that's about it, actually, to be honest. Forces, energy, momentum, and kinematics. It's not nearly as bad as it sounds because we've already learned all that stuff. We just need to figure out how to transform it into rotational versions and then figure out what that means. So I guess the first real thing I'd like to set up in your notes and have this in somewhere that you can come back to easily, because we're going to keep updating this. I want to put a table together of like all the quantities we were using. Like, so for example, in kinematics we used x for position or distance, displacement. We used v for velocity. We used a for acceleration. Excuse me. We're going to have versions of each of those for rotation. And today we're going to make a little table that has all the information in it. And leave some extra spaces in the table for things that were not there yet, like a lot of extra spaces. So, I'm going to call this first column linear. And this is going to be rotational. And you know what, we might as well make this a bit bigger. Yeah, ooh, I'm not good at drawing. We're going to have another column here for units for the rotation. I'll make that a little bit bigger. And conversion between them. So that's going to be our table for like variables and stuff. We're also going to have equations that are analogous. Oh, I've been talking all day and my voice is a little bit hoarse. Nay, a little hoarse. Get it? No? Okay. All right. So this table, we're going to start filling and populating it with fun stuff. There we go. So first things first, really the first thing we learned about was displacement. which was x for linear. I'm going to make a row for that, just for that. The rotational version is angle, or angular displacement, which we're going to call theta. Angular. Okay, couldn't quite fit it in there. Angular displacement is what that says. So if we're going to follow analogies, the units for linear displacement were just meters. Can you guess what the units for rotational displacement is going to be? Angular displacement? Radians. Yeah, exactly. Rad. Okay, and we need to figure out how to convert from a linear distance to a circular distance around a circle. So, how do you think we might convert from this kind of a distance to a circle, radius of r, and this is our angle theta. What we're really measuring here is this distance if you walk along the circle. It's that arc length. How do you think we're going to do that? Does anyone have any ideas? Pi is going to be involved. That's true. There could be. So 2 pi r is what of the circle? Is what quantity? The circumference. Right. Okay. So one way around the circle, the entire way around the circle is 2 pi r. So that's something. You have converted 360 degrees to a distance by doing 2 pi r. How exactly would you get any random angle? Literally any angle between 0 and 2 pi. Put it in terms of pi. Okay, maybe we're not seeing it. This angle here, the angle that we're starting to measure, our angular displacement, theta, is going to be in terms of pi. It's going to be measured in radians. And for the whole circumference, the angle is 2 pi, right? It's 2 pi radians. So really the conversion is just theta times r is equal to x. Or if you want to do it the other way around, theta equals x, your linear distance, divided by the radius of your circle. That's your conversion. So far, so good, I hope. Okay. Okay. Next quantity. As soon as you guys I'm going to keep watching you to make sure not everyone's done writing. Okay. Next quantity. It looks like everyone's done writing, as far as I can tell. The next row in the table is v for velocity. Angular velocity is omega. This little curly Q. I've had students call it Walmart before, but it's kind of like a curly W. It's a lowercase omega. I'm going to try to write that here. Angular velocity. If you say so. Can anyone guess what the units of angular velocity are going to be? Radians per second, yeah. Kind of like it's meters per second for velocity. It's radians per second for angular velocity. And can you guess what this conversion is going to be? Maybe you can't see a pattern yet. How about this? First of all, we defined velocity v as x over time. And we can also define angular velocity, omega, as theta over time. Does that help? Say again? That's exactly right. It's v over r. Can everyone see why that is? Maybe, maybe not. I'll go through it. So if omega is theta over t, right? Oh, I got an itch. And we want to convert, somehow get to v over r. Theta, the conversion we know was theta is equal to x over r. So I'm going to sub that in. So instead of theta, I put an x over r. And then we know that v is x over t. And we have an x over t. X over t. So really what we get is... since x over t was defined as v. So that's how we get to this conversion. I hope that was detailed enough for everyone. So far, so good. I like the thumbs up thing, Evan. Good job. We're ready for the next one? After... yeah. So I'm sure you can all guess the next thing. After displacement and velocity, we have acceleration. Oh my god, I am terrible at drawing straight lines. That is beyond embarrassing. Okay. The variable for angular acceleration is what it's called, is alpha, Greek alpha, which looks like a little fishy guy. No, that's kind of not a good alpha. Hold on. That's still not great, but I'll take it. Angular acceleration. And I'm sure someone can guess what the units are for angular acceleration. If the units for regular acceleration were meters per second squared, what about angular? There you go. And I'm sure you can also guess what the conversion is. Pretty easy, right? A over R. Not so bad. Alpha. Funny enough, alpha is the first letter of the Greek alphabet and omega is the last. If you know your Bible, you might know that. If you don't, you might not. Who knows? So this is enough. These three are enough for us to get going with equations of motion. I'm very pleased to say that time stays exactly the same when you're rotating. Otherwise, I'd be really disturbed. So we don't have to worry about converting time in anything. But just to kind of give ourselves a preview, what other quantities, what other variables we used last year do you think need to be converted or might need to be converted? Go ahead and throw any of them out. I'm going to write them down here and then I'm going to put them in order over there. Force. Absolutely. What else? What? Friction is a force. So it falls under this category. Not exactly. I mean, underneath the category of force or torque, I guess it would be called. I'm gonna just throw one out here. Oh, does someone have one? Momentum, absolutely. Oh, what goes along with momentum? What do we do in that same unit? Okay, energy, I'll just say it. Force, momentum, and energy all need to be converted. There's a couple other things, though, we haven't seen yet. The most confusing thing in this entire unit is converting mass. So, unfortunately, mass, when you're rotating, does not behave the exact same way. It depends on where the mass is distributed. So, for example, if I'm rotating my little pen here, even if it's the same pen, if I rotate it about the end, the mass behaves differently than if I rotate it about the middle. So not only is how the mass is distributed important, it's also where you're rotating around. What's the center of your rotation? I can see, Miles, you're playing with your pen there, right? It's a lot easier to rotate it like when you're grasping it through the middle than it is when you're grasping it by the end. It takes more energy to keep it vibrating there, right? So that's something called moment of inertia, and we're going to spend a good long time trying to get to the bottom of that when we get there. But thank goodness we don't need to get there yet. I'm going to put mass into our table here and give it its own row. Force also gets its own row. So does momentum. And I'm going to give kinetic energy its own row. Potential energy will stay the same, thankfully. And leave some more room down there just in case I'm forgetting something. But these are the big things that we need to convert. These are the big quantities we learned about last year. How's everyone feeling so far? Good. Uh-huh. Uh-huh. It's the distance depends on the radius. As you can see, the distance that you go depends on the radius of your circle. The r is in that equation. Yeah. It's not a very good circle, is it? Oh well. I gotta let go of my perfectionist tendencies. Okay, so I'd like you to keep this table readily available for when we update it in the coming days and weeks, probably, as we go through this unit. But today we just need those first three columns. So I'm gonna try to keep this page for us to keep going into, and I'm gonna start a new page here. By the way, I'm going to try my very best to post these pages that I'm writing on our Classroom. I'm really hoping that this thing saves them. I think it does. It has in the past, but you never know with computers, right? So we will see. I'm also going to try to post my recording of me talking on our Google Classroom so that you can always get to that. Okay. So now, instead of walking in straight lines, we are moving in, here's our radius, circles. That's not a terrible circle, except for my radius is kind of off-center. That's all right. You guys know what's going on. There's the angle theta. So, let's remind ourselves before we really start looking at this, what are the equations of motion? Anyone have their old notes from last year? Equation 1, 2, 3, and there were 4 and 5, but we never used them. We use them so much. I was hoping someone have them memorized. I do. Mm-hmm. Yeah. It would have been second unit after vectors. That would be part of the first equation of motion. Don't forget your initial displacement, right? Because you're not always starting at the origin, although a lot of times you are. So yeah, initial displacement plus initial velocity times time plus 1/2 at squared. That would be what I call the first equation of motion. The second one, yeah. Yeah, that's literally what I just wrote. Yep. No, it's good. It's good. You found it. Anyone got number two? You got number two, Kai? Hit me with number two. And of course, the whole point of all of these is that we're just taking it up to acceleration terms. If you want to get more complicated with the jerk, there would be a plus 1/6 jerk times t cubed. This is all derivatives, right? This is all increasing derivatives of the same quantity. And the same here, if it would be, plus 1/2 jt squared and all that. Okay, last one. V squared equals, anyone want to give it to me? Anyone else? I mean, anyone new? You all look so bored. Yeah, that's it. It's 2ax, not 1/2, right? Pretty sure it's 2ax. Anyone else have it in their notes? Make sure that I'm not losing my mind quickly. Okay. Yeah. And there are two more. What's that? Okay. There were two more equations of motion that, I mean, we could remind ourselves of, but I don't care. I never use them, and they're not honestly that great. They're just like, one of them is a modification of this to use the final velocity. I think it's like, isn't it minus v final? Whoops. Minus v final t plus 1/2 at squared. Isn't it that or something like that? Something like that, right? And then there's the other one, which is like a modification of, I think it's a modification of this guy, and I don't even remember what it is. I don't care about those two. I have never used them in my entire career of being a physicist, so yeah, let's not. These are the three we're going to work with rotation. Okay, so let's go through and see if we can replace all of our important quantities here. We know our conversions. I'll write them up here. Whoops, it was theta equals x over r, omega equals v over r, and alpha equals a over r. And what we're going to do is we're going to just sub in these things for our old variables. So for the first equation, instead of x, I'm going to write theta times r, right? Because I multiply that r over. Instead of x0, I'm going to write theta 0 times r. Instead of v, I'm going to write omega times r. Then I have to remember the t. Remember, we don't have to convert time, thank God. Anytime you have to deal with time is a real headache. And then for the alpha, I'm going to write, for the a, sorry, here, I'm going to write alpha times r. All right. We're almost all the way there. I also want you all to notice, that's exactly right. There's an r in every single term. It goes away. Doesn't matter what the radius is. Here we go. Whoops. Omega 0 times t plus 1/2 alpha t squared. That's our first equation of rotational motion. We could, if we were really pedantic, go all the way through the same way we did last year and derive that equation from first principles with all these new ideas. This is so much quicker, and like honestly, you guys have seen it, and I'm lazy. The best physicist is a lazy physicist. I'm sure I've told you this before, right? It means you do everything really quickly. You still have to get it right. Being lazy does not mean you can get things wrong. You still have to get it right. Okay, so that same way, we're going to just go through and convert all these things. Can someone even... I bet you can guess what this second equation of rotational motion is going to look like, just based on how this one worked. Anyone who has not yet spoken up want to give me a thingy bobber, a shot at it? We have 2 Hanaloris, and neither of them have cameras. It's kind of exciting. I don't know if I could handle 2 of them. So nobody who has not yet spoken wants to give me a volunteer thing? Okay. Steph, you were going to say something earlier and you got interrupted. You want to take this one? How about you do the next one? But I could not hear you at all, Stephanie. You unmuted, but I can't hear anything. Now you're muted again. I know, frustrating. Okay, it's all right. Evan, you want to give this one a shot then? Omega. It's like a W. Uh-huh. Yep. Alpha. Yep. Art. And then all the R's go away again. Yep. And you get to something that looks pretty familiar. Omega equals omega 0 plus alpha t. And there's our second rotational equation of motion. Numero trace. I bet you guys can really easily predict what this next one's going to be. I bet you we can even go through without the R's and just write down the final version. What do you think? Someone want to give me that final version? How about some ASMR? I'm going to scrape against the microphone. That was fun. Bella, you want to give us a shot? No? Okay. Hanalori? I'm just going through sequentially whoever's in my list. Didn't ask you, buddy. Go for it! Hit me! That's okay. Yep. Fish. Perfect. Perfect the first time. That's it. Those are our 3 equations of motion in rotation. They look very similar, I hope, to our old ones. And the way it works out is you just kind of substitute the new variable for the old variable. Mathematically, there is the R in there and they all cancel out because they're in every term, right? But it kind of just looks like you're substituting the old variable, or the new variable for the old one, which is kind of nice. It makes it, I think, a little bit easier to remember. Okay, we have about 20-ish minutes left in class. Let's do some really quick sample problems with these bad boys. I'm going to put up a new page. I'm going to write them all across the top. And there. So we're going to do some really quick sample problems with these just to get used to using them. Let's think about this. Hannelore is spinning scissors. So let's say she spins her scissors at a rate of let's say omega 0. She initially spins her scissors at a rate of, I don't know, what does it look like? Looks pretty fast. It's going to start at, let's say, 0.7 radians per second. And the final, oh, you know what? I'm not going to tell you the final. I'm going to tell you the angular acceleration she uses is going to be, let me take a look again. Let me see. Thinking 0.2 radians per second squared. And the time she is spinning for is, I don't know, 6 seconds. Why not? Oh, and you know what? We'll say theta 0, she starts at 0, just to make the calculation a little bit easier. Radians. First of all, let's find out how far in radians she spun the scissors. And second of all, let's figure out how fast they were going by the end. The angular velocity. Okay, excellent. And how did you get there? Which equation did you start with? 1, 2, or 3? 2. Okay. So omega final is equal to, we're going to say 0.7 plus alpha is 0.2 times 6. So omega final is, I don't know, whatever that is. What's 0.2 times 6? 0.1 times 6 is 0.6 times 2 is 1.2. So 1.2 plus 0.7 is 1.9 radians per second. Did I do that right? Make sure I did that right. I did it really fast. I know, buddy. So that's the final angular speed she got it up to. For figuring out the angular distance, the angular displacement, we need to use equation 1 to find theta. Or I guess we could use equation 2 now that we know omega. But, I mean, we can do it both ways. This is the way I would do it. This is what I would do first, anyway. Theta 0 was 0. Omega 0 is 0.7. T is 6. And 1/2 alpha was what did I say? 0.2? I said 0.2. And T was 6 squared there. So let's see. I have a 0. Oh god, 0.7 times 6. I'd probably do that in my head. 3.6 plus 0.6, right? Am I doing that right? So 4.2. Yeah. 4.2. Half is 0.1. 36, so plus 3.6, right? So it's going to be 7.8. If I did that correctly in my head, which I very well may not have. I was trying to do it as quickly as possible. Just going to wait for someone to verify that I did that correctly. I guess I can do it this way too. Omega squared. Well, I know omega. It's 1.9 squared is equal to 0.7 squared plus 2 times 0.2 times theta. There's a lot of squareds here. I don't like it. 2 times 0.2 is 0.4. Let me bring this down here. 1.9 squared is going to be a little bit less than 4, right? I don't even know what it is. 3.9 something. I don't even know what it is. 9.1. That's definitely wrong. 3 point what? 6.1? I believe that. 0.7 squared is going to be 0.49, right? Plus 0.4 times theta. 3.61 over 0.49 minus 0.4, or sorry. I did that completely backwards. 3.61 minus 0.49 over, did not mean to do that. Over 0.4 is theta. There. God, I don't want to do that in my head. That's ugly. It actually ends up being 3.12 over 0.4. Ugh. It should, yeah, which is what I got before. It's a good way to check and verify, though. You know what? I have a calculator right here. Let's not be super pedantic. Let's just do it. Hey, it's 7.8. Look at that. Whoops. If I could write a 7, maybe I would be happier. There. There we go. Okay. And so that's a nice verification, at least, that we did both of those correctly. And I guess, one other interesting thing we can do with this is we can convert it, if we know the radius, we can convert to sort of measurements we're more familiar with. So, Hanalori, let's see those scissors again. Hold them up. Your head is an object that I am familiar with. I would say those scissors are, I don't know, 15 centimeters maybe? Anyone else disagree? Anyone want to say 14 or 16? It's fine. It doesn't really matter that much. Yeah, let's say 15 centimeters for those scissors. So in order to convert back, we need those conversion equations. And we're not going to do alpha. I guess I don't really care. We're not going to do alpha. So to get x from this, I need to multiply both sides by r. And to get v from this, I need to do the same thing. So 0.15 times 7.8. And v is going to be 0.15 times 1.9. Again, I could do this in my head, but boy, I'm going to be lazy. 1.17 meters, and v is 0.285 meters per second. So, what this is talking about is not the entire scissorators. We're talking about the tip. The point of the end of the scissors has moved 1.17 meters, and the velocity, by the time she's finished accelerating it, is 0.285 meters per second, which is probably enough to put an eye out. Good job, Hanalori. It's super dangerous. Thumbs up. If you wanted to measure the velocity of some other point on the scissors that's not the tip, it's moving the fastest, or you wanted to measure, how far, say, the handle part of the scissors moved, you'd have to use a different radius, right? I used the full radius of those scissors. So if I draw a scissors here, there you go. She's rotating around this point here. So this R that I'm measuring is really from her point of rotation up to the end of the scissors. But for example, if you were interested in like the little rivet that fastens the scissors together, and you were interested in how far that thing moved, you would take this radius instead and use that in all these calculations. And what you'd get is it would move a smaller distance, and it would also be slower. When this thing is, rotating, if we simplify this, we just have like a straight rod rotating about its end. You can kind of, I think, intuitively see that something right at the pivot point is not really moving at all, whereas the end is moving quite a lot. So whatever's at the end of the rotation is going to have a further distance to move. And because of that, since it happens in the same amount of time, it has to move faster. Okay. We've got about 10 minutes left in class. How's everyone feeling about this? It's a pretty gentle introduction. Nothing too hard, I think. But if we're feeling freaked out, it's a good time to take a little break. You all look like you're asleep. I mean, me too. Let's be honest. You definitely could. Why don't you do it for us, Miles? Yeah. Well, you know what? Let's look at that just as a test case. Why not? We have a rivet here, which is the center of our rotation. And, I mean, what do you call one half of a scissors? A scissor? So there's your scissors. And let's say, I don't know, you're closing this distance with your hand, right? What does that angle look like to you guys? I'm going to say, yeah, 70. Why not? 70 degrees. Oh, are you going to convert to radians for me? Well, pi over 4 would be about there, right? Pi over 2 would be about there. So between pi over 2 and pi over 4. Did someone else say something? I might have talked over them. 7/8. 7/18. Beautiful. Why not? Miles, you know me. I love using the ugliest possible numbers in my example problems. Just to give you guys fits, you know? I want to make sure I'm not going to minimize my thing accidentally. Okay. All right. So that's the distance we're closing. How long? It didn't take Miles very long to close those scissors, right? It was like 0.05 seconds. I mean, that's just a really bad. Don't, Miles, stop. I want you to have all your limbs. Maybe he could get into... Right, exactly. Mm-hmm. It's true. It's... I believe it. So I'm going to have an R1. Oh my god. No. Do not have that as a takeaway. I'm going to have an R1, which goes from the rivet, our pivot point, our center of rotation, out to the handle where you're rotating it. And I'm going to have an R2, which goes from the pivot point out to the end of the scissors. So, I mean, what does that kind of... Hold up your scissors again, Miles. Let me see them. Oh, you measured. Centimeters. That is not correct. I'm gonna say 3 centimeters is what that looks like. If the blades are 9, because it's not to the end of the scissors, it's to where you're holding it and applying the force. Yeah. All right, I'll take 3 because that's what I said. Meters. Okay. So let's see. So we know the angle there. We know the time. We know radii. So let's figure out velocity, I guess. Omega and v. Omega, remember, was equal to omega 0 plus alpha t. I'm going to say omega 0 is 0. You start at rest, right, in so many of these problems. So we can figure out, I guess there's too many unknowns. Oh, no. Maybe we need to start with the first equation. I'm sorry, guys. Plus 1/2 alpha t squared. Okay. So we know theta. You know theta 0 is 0. Omega 0 is 0. We know t, so we can actually find alpha this way. That's good. That's something we need to find. Okay. Theta is 1/2 alpha t squared. Alpha is what we're going to find, so 2 theta over t squared is our alpha. So 2 times 7/18 pi all over 0.05 squared, which is going to be some really ugly math. 7 over 9ths pi over 0.025. Good Lord. We have done some horrific things math-wise here. 7/9 times pi over 0.025. I get alpha is 97. That's pretty big. I'm going to round 0.74 radians per second squared. We can then plug that into here to find omega final. Times 0.05. So yeah, omega 0 was 0. Alpha we just found 97.74-ish. 738433811. And 0.05 seconds was the time. So I'm going to do that right now. So my omega final that I get for this is 4. Rounding up again, 4.89 radians per second. So these are true. This omega final, this alpha, and this theta are true for both sides of the scissors, no matter what the radius is. Right? They both have the same angular properties, but because they're different radii on that circle that they're traveling, they're going to have different linear measurements, I should say, not properties. So for the side of the scissors that you're holding, this side for R1, theta is x over r. So again, I know probably some people are getting bored of me showing this, but I'm just showing it so everyone gets a chance to see the real simple math behind it. The distance that you're traveling, I'm going to call it x1 for your fingers that are actually traveling, is going to be theta 7/18 pi times r1 0.03. So the distance your fingers are traveling, little fingies, times 0.03 is 0.037 meters, so 3.7 centimeters. Whereas x2, if we're doing it the same way, for the end of the scissors, is going to be somewhat bigger. Times 0.09 instead of 0.03, we get for the end of the scissors, it's going to be traveling 0.1, if I round, it's going to be 0.11 meters, 11 centimeters. Okay. Significantly farther, even though the angle they travel is exactly the same. If we do this in the same way for omega, I can't write, you guys. It's been a long week already, huh? V is omega times r. And omega we just found right here. This is omega final. For V1, I'm going to plug in these numbers for us. 4. Oh, you know what? I'm going to go find the exact one on my calculator real quick. 4.886, whatever. Times, for V1, for your fingers, it's going to be 0.03. And that is, your fingers are moving at a speed of 0.15 meters per second. For V2, for the end of the scissorators, it's going to be moving at significantly faster, 0.44 meters per second. And that's just because they have the same angular acceleration and speed and displacement even, but because they have different radii from the center of rotation, they're going to be moving at actual different linear speeds and have different linear displacements. Okay, we're 1 minute away from the end of class. Are there any questions I can answer before we go off and you have a nice weekend or your last class or whatnot? What does everyone have last block? Band. That's good. Band, choir, drama. Who has English? Well, okay. That sounds good, you guys. Sounds great. I hope that this was pretty clear. Or at least we'll get there eventually. Yeah. And I guess have a great weekend, and I'll see you on Tuesday, right? Tuesday. On Tuesday, we will continue this idea. Look out for a video from me, hopefully by Monday night, on this kind of topic. See you guys. Will do. I won't leave. I'll hang out. 0.11 meters. Let me go back to it. Let me reshare that screen so we can see it together. For X2, I did the same way I did this guy. I don't know if you can see my mouse, right? So no, it's X2. So X1 is 0.037. So X2 would be 7/18 pi, the same angle, theta, times the 0.09 radius instead of the 0.03 radius. And that'll get you to 0.109, or I forget exactly what it was. But it rounds up to 0.11.